All right. Hello, everybody. Can you hear me? I don't know. Hello, everybody. Can you hear me now? Okay. Can you hear me now? It's on, but... Okay, perfect. Thank you. All right, everybody. We are at the top of the hour, so we are going to get started. All right. Thank you very much for being here today. Today, we have presentations from 4 of our new postdocs on STScI. So we have Vital, Avery, Ben, and John, and they will be introducing the research, and they're going to be introducing what they did in the PhDs and what they are doing here. So we are going to start by Vital Fernandez. Vital is a postdoc at ST, working in chemodynamical properties of star formation regions with Fernandez and Linda Smith. Vital did his PhD in astrophysics in the Illinois in Mexico, a postdoc in La Serena, and a postdoc in the University of Michigan from 2023 to now. And now he's here, and he's going to be introducing his research about aspect, an algorithm for blind redshifts and line measurements. So let's welcome Vital. Thank you.
Thank you. Hello, everyone. First of all, I want to thank the organizers for inviting me to this colloquium, and all of you for the warm welcome here at the Space Telescope for the past months. And I would like to enjoy this opportunity to present the work I've been doing on this algorithm for the past year as my contribution on the CEERS and CAPER surveys. And it's now a model that we can publish for the community to enjoy. The purpose of this paper is to teach how we can use machine learning to recognize these patterns in astronomical spectra. Basically, we want to distinguish the continua from the lines. And why are we interested in doing this? There are 3 reasons. First, we want to identify and do statistics on highly desirable scientific targets. For example, over here we have H-alpha line for the Rubis survey. And even though this is a small sample, it would be nice to have a reliable and powerful way to apply to detect this kind of profiles in large orbits such as DESI. The second reason we need this algorithm is to manage bad data. For example, over here we have some example of the non-lines spectra from the CAPER survey. And from my own manual review, there is like 40% of the objects, either because they are low redshift featurely continua or because they don't have this, the high to noise signal to noise ratio, we cannot detect any spectroscopic features. So we need a powerful and reliable way to diagnose these objects because they take a lot of time from the scientific research. And finally, now that we are all enjoying this big data astronomy age, we need new tools to even manage the simplest operations. And when we get a spectrum, the first thing is to measure the redshift and get a quantitative idea on the line fluxes. And that's what we're going to do in this paper. And to show you an example of how this works, I have this observation of the NGC 628 galaxy from Linda Smith and collaborators. And this website, it's a platform I developed to distribute the measurements from the CEERS and CAPER surveys, and also to showcase some of the functionality from these algorithms. So for example, we're going to load the spectrum. This is a text file. Oh. This will be here. Oops. This one. Open. Reload it. Here it is. And now we're going to run aspect. So in here what we have is the observation. In pink is the continuum, green are the lines, orange are the absorption lines, and yellow are these cosmic ray-like features that were not cleaned by the pipeline. And over here we have on red, we have this white noise. The PAH has not been recognized because it's not one of the pattern of the algorithm. So this is one of the issues. But as you can imagine, once that we know what each of the pixels, what kind of classification they have, the analysis becomes much more simpler. So how does this work? So this presentation has two parts. The first one is the algorithm design and training, which is surprisingly easy. And then the second one is how we implement it on real data, which is surprisingly hard, mainly because we need to standardize all the things that we may or may not know. Fortunately, we have two plots that will help us with each of these phases. The first one is this parameter maps for the features, for the dimensions of a line that we published in Fernandez 2024, the line paper. On the y-axis, we have the amplitude of the line divided by the noise on the continuum. So basically, this is the signal to noise. And over here, we have the velocity dispersion in pixels, the Gaussian, the sigma of the line, and the instrument resolution. So we can use this parameter map to divide different type of features and generate synthetic lines. We can see this here. For example, in this region, we have narrower and weaker lines, and as we go this way, we have wider and more intense lines. This region would be the continuum. If we are mod noise, we will have white noise, and then we can get creative and say this is a cosmic ray, and we can add more regions. And if we take the negative version of these shapes, we would have absorption features. So each of these points is a line, and we feed that into the machine learning algorithm. These are the parameters of the random forest. And the only thing to keep in mind is that in machine learning algorithms, the data must be scaled between 0 and 1. But for some of these features, we want to keep an idea of the intensity. So this, the difference between the maximum pixel value and the minimum one, we keep that as a feature for the algorithms, and then we use that in the training. But also when we want to run the detection, we must also keep this scaling. And over here, we have the confusion matrix for the results. To explain it, what we want in this kind of plot is the diagonal to be as high as possible. That means that the predicted class matches the actual class, and on the sides of the diagonal, we might have low values. So you can see that we have some issues, that some cosmic rays are identified like emission lines. This is this region over here, but overall, it's very good. However, there are some issues which cannot be diagnosed with these ratios, such as the fact that when we input one shape that was not, the model was not trained with, it will be assigned to whatever. But we will discuss later how to deal with these issues. And on the paper, you will have the algorithms to run, to generate this training sample. Aspect can be installed from pip, but it's also very important for us that we have a working algorithm for the community to use. And this will be integrated in Lime. Lime is a package that we published in 2024 for the analysis of lines, either in long slit, IFUs. We can fit multiple profiles with different shapes. We include functions to open spectra, to plot the data. We can manage the uncertainty. We can include mask, and we have a very detailed documentation. The video is a bit outdated, but if you're interested in using it, please tell me, and I can present it to you. So that's as a side note. So part 2, how do we implement it? Now, one of the issues with machine learning is that we are very constrained by the number of features. How, in this case, would be the size of the box with the detection for the line. And in the literature, there isn't a model for the line bands which can accommodate all the wavelength range that we can observe with the James Webb, from the forbidden lines, semi-forbidden lines on the ultraviolet to the PAH on the far infrared. So we are proposing this model on the paper, which may actually be the most important thing because it helps us with many things. On the x-axis, we have the resolving power of the instrument. For example, James Webb, we have here the Deci Sloan, X-shooter, and on here we have some of the velocity dispersion for some targets of interest. For example, we have H2 galaxies between 30 and 70 kilometers per second. We have green P galaxies, the pearl component, AGNs, and we can expand this to the right with planetary nebulae or stellar atmospheres absorption lines. And from here, once we know the instrument that we are using, the range of velocity we're dealing, we can get the number of pixels that feature is going to cover. And then we can feed that into we can use that to select the training sample that we need, and then we have the optimum sample for our algorithm, for this kind of objects. Now, I will not bother you with how we implement Aspect online. There is something just important to remember, and it's that even though this training model is visual, we are basically giving the shape of the features we're interested on. The application on line is more like Braille. We're moving 1 pixel at a time. We run Aspect 100 times to account for the uncertainty, and then we apply a series of decision matrices to resolve the conflicts. And this may seem like an overkill, but the operations themselves are very simple. We can apply this for 1D, and as long as we have the memory and the processors, we can go to D, we can apply a Muse cube, or we can apply it to the DESI survey, because the algorithm will be the same. So now we know where the lines is. How do we measure the redshift? This is a methodology I developed alongside Kevin Hart at the University of Michigan, and what we do is that we introduce a series of lines that we are expected. For example, that would be H beta, the O3 doublet, H alpha, the S2 lines, the helium line at 10,000 angstroms, and we apply a brute force approach where you're designing the bands with the method we described before, and we can either sum the flux that passes through these bands at each redshift, or we can count the pixels. We have 2 methods for the price of 1, and that gives us the expected redshift of the object. For example, over here we have, this was one of the observations from last Friday. This was a redshift 17 candidate from Capers, but unfortunately it's lower redshift. So now we know the redshift of the objects, but for posterior chemodynamic analysis, for us it's very important to keep track of the transitions involved in each line. And that can be difficult in the case of the high, when we have a wide range of redshift values, and in the case of the prims, also the resolving power changes. So we don't know what the line is going to look like a priori. So to resolve that, we present in the paper this methodology in which, since using the method we know before to define the bands, we know the pixels covered by each line. From here, we can calculate the gram matrix, which tells us how many pixels in common each line has, so that gives us the groups. And then from the ratio of the separation between the lines and the velocity dispersion, below 2, they are merged, they cannot be deblended. Above 2, they can be deblended. We compare that to the input lines we expect. This is, for example, my configuration from 4 Capers, and from there we can establish which lines can be deblended in the posterior analysis. And now that we know which lines we are measuring at this point, we have here an example using the DAN project, which are galaxies from the different surveys with the PRIMS dispenser. And this is with the pixel sum and with the flux sum. So in the case of the flux, we have an 80% true positive. In the case of the pixel sum, we have 39. And now what we're trying is to minimize these cases in which we have, from both methodologies, a false detection. And that will allow us to make tiers of the accuracy, so we can say when we measure several, in case we have 4,000 galaxies, we can say, okay, in these objects we don't detect any line, in here we detect only line, in this one we have 1 redshift from 1 technique, and in here we have from both techniques agreement. And finally, on the paper, we are also going to discuss how to measure line fluxes using machine learning, and in practice this is not very useful because once we know the pixels each line is located, we can easily use traditional techniques. But it is well known from the literature that for lines which are very weak, we are overestimating the measured fluxes because the noise is contributing to the observed shape. So we are hoping that we're exploring the possibility that since now we have 3 methods to determine the flux of the lines, we can recover the original values, or at least obtain a better estimation. And that's all. Thank you very much.
Thank you very much. We have 1 minute for questions for Vital. Dan?
Hey, great talk, excellent work. So you showed sort of at the beginning there's a lot of these spectra that come out and you just can't really tell if there's lines or maybe there's some wiggles but you're not sure. and then someone will go get a 60-hour spectrum, and all of a sudden you can see the lines. Can your machine learning do any bit of a better job with those other noisier spectrum, maybe find some lines that understand?
It's at this point, what we can do with this method that cannot be done visually is to take into account the uncertainty on the flux, to repeat the analysis and see what shaped results. And it gives us some confidence on see if there is a really line there. The idea now is that in those cases that maybe there is a line or not, if we have different methods that can predict the flux of the line, try to compare them and see if there is some way to restore an upper value. But yeah.
All right, we need to move on, but Vital is going to be around, so you can always talk to him. Let's thank Vital again. All right, in the meantime, I'm going to be introducing our next speaker. So our next speaker is Avery Kim. Avery is a joint postdoctoral fellow in the ISM and Milky Way Halo group at STScI. Her research focuses on the understanding of multi-phase, multi-scale interactions of gas and dust in and around galaxies, and how these processes shape a galaxy. Avery completed her undergrad degrees in physics and astronomy at the University of California, Berkeley, and received her PhD in astronomy from Columbia University. All right, Avery, take it away. Thank you very much.
Hi, everyone. I'm Avery. Today, I would like to share some of the work that I've been doing since I started here, which is to develop a scalable pipeline for UV absorption spectroscopy. Before I jump into this, I want to first discuss some of the background of why I'm doing this. UV spectroscopy is one of the most powerful tools to study diffuse baryon in the universe. And as you already know, the UV wavelength hosts many of the key atomic and molecular transitions that trace neutral, ionized, hot and warm gas across multiple scales, interstellar, circumgalactic to intergalactic scales. Due to its high sensitivity, it is also able to measure very low density gas, which are not visible in emissions. Here are some of the list of the science that can be enabled by UV spectroscopy. The one in the bold are the ones that are related to my current science program. To briefly talk about illustrate the absorption features, let us consider this simple picture. A light from a star, oh, I cannot really see my pointer. A light from a star travels towards the telescope, passing through multiple cool clouds along its line of sight. The spectrum that you see on the left side is a stellar spectrum, this probing the one of the Milky Way star, and each gas cloud along its way imprints a unique absorption signature at different velocities or wavelength. If there are multiple clouds along its way, in this case 3, we expect to or observe the 3 those absorption features, what we call as components, in multiple lines, in this case chromium-2 and iron-2. This gives you some of the ideas or backgrounds about one of the ways to measure column densities from UV absorption, which is component fitting. Assuming that the UV absorption can be modeled with bulk profile convolved with thermal broadening and natural dampening, the component fitting approximate observed profile as a sum of finite number of discrete velocity components. If done correctly, this provides most physically informative, but it is model dependent. The individual components that you see in this component fitting model are often recognized as one cloud for each component, or the sum of multiple groups of clouds. As you see, this requires spanning high dimensional space. Therefore, it is computationally expensive. The other method, such as AOD or curve of growth, are not resolving individual velocity components. It instead rely on quantities integrated over velocities, which is computationally cheap, but in cost of losing information about kinematics of individual gas clouds. I'm choosing the component fitting method because they are relevant for the science project I'm interested in, which is getting the per cloud variances for chemical abundances and dust depletion. As I mentioned, component fitting method is quite computationally expensive, therefore hard to scale. The plot on the left-hand side shows number of absorption sightlines analyzed per paper since 1990s. As you see, most of the absorption studies has focused on smaller number of components, a small number of sightlines due to its high computational cost and perhaps high observational cost as well. There are two primary bottlenecks in component fitting, which are continuum normalizations and component identification. Due to the blending and the saturation, one has to look at multiple lines in order to get the correct components. Doing this correctly and uniformly scales very poorly as sample size grows. And component fitting process can also be subjected to degeneracies and human biases. This has been traditionally done by human hands, whose model choices can be naturally influenced by human judgments. However, this is a pretty difficult problem. For example, for these two cases, how can we tell which one is a better fit or has a better component structures if two have similar chi-square? This kind of motivated me to think about developing an objective framework for model comparison. With HWO coming online, we expect a substantial increase in both quantity and quality of UV spectra available for science. To fully capitalize the available data that is coming online, what we need is a fast, scalable, and statistically rigorous pipeline for analyzing absorption spectra. I have been focused on optimizing two bottlenecks, which are continuum normalizations and component identification. For continuum normalizations, I intend to include theoretical model in a more systematic way. For component identification, the goal is to get more objective criteria for determining the best model on top of the automation. For interest of time, I'll probably skip through continuum fitting and jump right into Bayesian component fitting. We use dynamic nested sampling to model the individual velocity components of UV absorption spectra. The nested sampling is one of the Bayesian inference algorithm whose basic idea is to draw points or samples from the prior and systematically replace the low likelihood samples to high likelihood samples to fully map the posterior distributions. The dynamic nested sampling is an upgrade from the nested sampling because it uses the adaptive allocations to maximize its effort to map the posterior more effectively. For our component fitting algorithm, there are four inputs, four separate categories of inputs, which are parameter priors, V indicating the velocity centroid, B indicating Doppler width, and column density, log n. We also input line information, which is wavelength, oscillator strength, and damping constant, and line spectra, individual line spectra, and their associated per pixel error estimate. And then the sampler outputs the posterior distributions of per line continuum and per component velocity centroid, Doppler width, and column density. And it also outputs something called Bayesian evidence, which gives us better objective criteria to choose the best model. Things has been working pretty well so far. On the right-hand side, I'm showing you the individual fit result from our fitter. This example is looking at iron 22240. On top is one component model, increases to 2, 3, and then ends at 10 component model. But we actually evaluated until 20 components. Here, the gray points are indicating the data, the observation data. And then you see that the dashed lines, the colored dashed lines are representing the individual velocity components, where the blue thick lines are the sum of all these individual components. The small rectangle below this plot is representing the residuals between the sum of the model, the sum of the model, which is a blue thick line, versus the observation. So this kind of brings us back to the questions that I was asking earlier. Amongst all of these 10 models, and you see that up to like starting from 5, it becomes really hard to tell which one is better model. The question now is, among all of these 10 models, which one is the best fit? My approach to answer this question is Bayesian evidence. The Bayesian evidence is integral of likelihood and prior, integrating over full posterior space. So this is act as the Occam's laser that is balancing between goodness of fit and model complexity. So like in here on the left-hand side, I'm showing you the plot of the number of component model versus the log evidence. In this scheme of things, you see that the 10 component model is evaluated the best model because that has the highest evidence. So in other words, this 10 component model is what we see as the model that has simplest model but has good fit. In this way, we're able to quantify our model choices. Another advantage of this approach is that we are able to quantify uncertainties in a robust way. Here, I'm showing you some subset of the posterior distributions. This is the 4-component model for central velocity, Doppler parameters, and column densities. Because we have full posterior distributions, we can get well-defined uncertainties and covariances. Of course, the robustness of the results are depending on various factors. Here are the 5 factors that are most influential for our model. Of course, we have to have good continuum fitting in order, especially where we are taking care of the multi-line analysis. High spectral resolution is also important as it significantly improves the ability to resolve the component structures. Realistic covariance matrix and per pixel error is also meaningfully affecting our posterior distributions. But in practice, two most influential factors are this prior choice and number of points in sampler. If we don't have enough number of samples in the nested sampling, the sampler is not effectively mapped the posterior. Also, the nested sampler is depending on the prior to explore the parameter space. It depends on the prior choice. Here are some examples of priors that we are using. We are trying to be unbiased as possible, so we are using flat priors for column density and the velocity and continuum. But for the width, we are currently using gamma function. But this is not settled. We are experimenting different prior as well. So to summarize, I'm developing a fast and statistically rigorous analysis tool for absorption spectra. The immediate application to this is component level analysis for column density, and we are able to also explore the gas kinematics at a cloud level and drive the chemically meaningful abundances and thus depletion patterns. This will further enable reproducible component fitting, robust model comparison, and uncertainty propagation, and leads to scalable analysis for UV archives and future missions. I'll stop here and take questions. Thank you.
All right, thank you very much. Questions?
Thank you for this talk and developing this tool as well. I had a question on the slide which you just showed, like prior to this one, where, yes, this one, where you have gamma function as b prior and a flat function as log n prior. And you mentioned that you can use different priors as well. But since you are using this one, is there a scientific motivation? If you are, is there a scientific motivation for studying this thing? And if we are using different objects, do you recommend to use different priors?
Yes, so these are, well, I want to say the bottom line is we're trying to go towards the flat priors because we don't want to bias our results. And we see that the results are really affected by the choice of the prior in a way. We can cover it with a third piece, but we want to get the optimal answer as possible. The reason that we chose gamma function for B prior is that we want to have the wide range of the wide range of B parameters, like up to 50, because there are very warm gas exist. But then most of the components that we see in practice are very narrow. So, and gamma function was one of the prior that really covers the parameter space well. But as I mentioned, this is up to kind of experiment right now, and we're exploring different prior choices.
All right, thank you very much. We need to move on. Let's thank Avery again. All right, while Ben gets ready, I'm gonna introduce him. So now our next speaker is Ben Gibson. Ben Gibson studies galaxy evolution, stellar population, and interstellar gas and dust using both resolved stellar photometry and integrated light spectroscopy of nearby galaxies. He did his undergrad at Florida State and received his PhD from the University of Utah, in which he developed a novel approach to analyze high-resolution integrating light spectra of M31 from the Apogee survey. In his postdoc, he's studying resolved stellar photometry of M81 and other nearby galaxies from JWST and Hubble, proving the interplay between these galaxies' stellar and dust content via SID fitting. All right, Ben, you can take it away. Thank you.
Thank you for that lovely introduction, and thank you for the opportunity to come speak today. So my slides keep advancing forward, so you can see that spectroscopy and photometry probe different. What the heck's going on? Pause. X? Okay. Don't autoplay. All right. So hopefully this will stay. I am a bit of a spectroscopher and a photometer, so I'm excited to talk to you about both things today because, as this first slide now says, we probe different physics, and we need both of these types of data and both understandings of physics in order to gain a more holistic understanding for the stellar populations in external galaxies that, again, is not accessible from either. So to show this, I have a quick demonstration. This first plot here shows CMDs and compares them across 3 different distinct recent star formation patterns. So you'll see here in the middle, we have a very bursty, sort of segmented star formation history. In the middle, you have basically quiescence up until about 100 million years ago, where we ramp up, and then we have a much slower ramp up over those last 500 million years. And we can see distinct differences in the CMDs of these simulated star formation histories, namely like the ridging along the branch here in this CMD. And so there's a lot of information encoded here, and we can really tell the differences between these stellar populations just by their CMDs in these different star formation occurrences. But if we are then to take this stellar population and simulate it as a near-spec spectrum, we can see that it looks like this for this center plot here. But then if we look at the one over on the right, where we have that much more ramped star formation history, they're basically the same. So we can try and toggle between these a little bit, and I'll tell you right now, there's about a 1% difference. So not only can you not see these by eye, no real spectral fitter is going to be able to tell the difference here either. And so to be able to probe that star formation history, we need the CMD. On the other side of this, however, if we want to probe chemical information, we need the spectrum. So this plot here is the alpha bimodality plot that we see in the Milky Way, where we have a distribution of stars in their metallicity and alpha abundance, and we can see there's this high alpha over density here and a low alpha density here at higher metallicity. And so if at one metallicity, say 0.5, we have an over density at low alpha abundance and a overdensity at high alpha abundance. And this plot has only been made in the Milky Way, and it's only been made because we have observations of hundreds of thousands to millions of individual spectra of individual stars throughout the galaxy. And so this kind of information cannot be gotten using CMDs, unfortunately, because of the information contained in individual spectral lines in each one of these stars. So making this fact even more complicated, if we look at other parts of the galaxy, this distribution changes. So in this solar neighborhood here, we can see we have two densities at different metallicity and alpha abundance. But if we zoom out, we can see that this changes wildly depending on where you look. Like in the inner galaxy, we only have this low alpha, high metal population, but if you zoom out, it's still low alpha, but at much lower metallicity, etc. So we need to be able to decompose our spectra into, we need to be able to decompose our stellar populations into different overlapping components that vary with respect to location within the galaxy. So like I said, this is only gotten from spectra, and we can't tell what's going on if we look at integrated light because everything's just going to get blended together. You can't fit a chemical evolution history to this plot. I've tried. So we need to get a little bit more creative. And so this is what I spent my thesis working on. And so I was trying to basically, again, decompose integrated light into multiple components using some data from M31. So this data in particular is from the Apogee survey, which normally was looking at individual stars throughout the Milky Way galaxy. But instead we pointed it at M31, kind of turned it into an IFU for a few nights, and got data covering about the inner 7 kiloparsecs of the galaxy. We also took Apogee's regular library of stars within the Milky Way galaxy, turned them into SSP templates that we can use to analyze our integrated light data, and these span a range in metallicity, age, and alpha abundance that's seen in the Milky Way, which allows us to directly compare our results to what is seen in the Milky Way. And then we do spectral fitting, very standard routine here where we're just shifting and broadening lines to fit our data to our models, or vice versa. And then we throw all of this into a big MCMC. There's now, I guess, the third different spectral fitting routine that you guys have seen today. So we're trying to fit all of our data to our models using MCMC, and we get a velocity, dispersion, metallicity, alpha abundance, and age of these stellar populations in our external galaxies. So when we did this in M31, we first did it with one model each, and we were able to map the chemodynamics of the stellar populations across this galaxy. And the main sort of result that I want to point your eye to here is this metallicity plot here, where we can see that the bulge has a distinctly lower metallicity than the rest of the disk. This kind of threw us for a loop for a little bit because looking at external galaxies, disk gradients tend to be negative. And so this positive gradient was really kind of confusing us until we rationalized that this is really just a mixing of two different stellar populations, right? If you have a uniformly metal poor-ish bulge and a uniformly enhanced disk, all you have to do is say that the amount of light coming from each one of these components changes as you move out, and therefore you're going to get this positive gradient. And so again, that helps reinforce the fact that we need to be able to break down these stellar populations into two components. So that's what I did for my next paper. And we took this same MCMC model. We have now expanded the fitting routine to cover two different stellar templates. And we can now characterize two populations individually. In order to do this, though, we needed to constrain our fitting a little bit. And so we first took this exact image of M31 from the Unwise program, and we fit a photometric decomposition model to this. And so we were able to take this and break it down into a bulge, a bar, and a disk. And this gave us two capabilities. One, we could look for regions in the galaxy dominated by just two stellar populations, as well as knowing how much light is coming from each one of those. And then we can also use this to identify where those two populations follow a set of physically motivated kinematics priors, where we're basically saying that in these regions of the galaxy, we have one component that is slower rotating and has a higher velocity dispersion, and then the other one is faster rotating with a lower dispersion, basically just saying that this component 2 has more structured rotation and more structured kinematics than the first one, which will be more dispersion dominated. So when we did this, we looked just in the inner kiloparsec or so in the bulge, and we were able to then find intrinsic gradients in the bulge and bar components by themselves. And so the most significant result out of all of these points and lines and everything that you see here is this metallicity gradient here. This blue one indicates that this is for the bulge, and we are seeing that it's positive. So whereas before we were seeing a positive gradient that could be rationalized as just a mixing of two different populations, here we're able to actually zoom in on this very inner region and see that this positive metallicity gradient is in fact intrinsic to the bulge and not just due to a mixing of populations, which then starts to give you an indication for what might have happened in the history of this galaxy. It could say indicate that the bulge formed inside out. We don't have great star formation histories. Obviously, we're just looking at spectra for this. So we would need to break this down into more complicated data in order to get a star formation history. But again, we're starting to reach a higher level of complication and of detail in these populations. The other location where we found a cool result was in the northern part of the disk here, where we did the same thing. We broke it down into two components, and we found that one component has a much higher alpha abundance than the other, and that their kinematics are distinct. And this is pretty similar to what we see in the Milky Way. Maybe not quite an alpha bimodality, but seeing those two different kinematically distinct populations with distinct alpha abundances is kind of a smoking gun for this sort of thick and thin disk dichotomy that we see in the Milky Way. So this was an exciting result to see that we can have distinct components that we're pulling out of the same thing from here. We didn't see this in the south, and that's just another bit of indication that something is going on in the south of M31 that's interesting and needs more work to be quantified. It might have to do with M32, but that's an active field of research right now, trying to figure out why there's such a difference between these two parts of the galaxy. So that was a lot of spectroscopy. Let's move on to photometry, because that's what I'm doing now that I work here at Space Telescope. This is a 3-color image here that Chris Clark made of archival JWST data that we are analyzing with the BEAST. So we're going to do some SED fitting, try and figure out what's going on in this galaxy and in a couple others, figure out why they are so interesting. So NGC 4449 as well as 7793 are two categories of galaxy that have been given the moniker Badgers, which are blue and dusty gas-rich sources. I have a very highly scientific diagram here of what that might look like. And these blue and dusty gas-rich sources are a bit of a galactic contradiction. They have really high dust to stellar mass ratios. They're very UV bright, but also dust rich, which doesn't make a lot of sense. And they're very poor in molecular gas, but also star forming. So they're forming a lot of they're forming a lot of stars, producing a lot of UV emission, but they have a lot of dust to form those gas. And they exist kind of in the same area. So we're trying to figure out exactly what's going on with these Badgers by taking a look at two of them in their resolved stars. So these are the specifics of these galaxies, and we have data from the archive from both Hubble and JWST for both of these galaxies. Here's the data coverage. And like I said, we're going to do SED fitting to all of this, which I'll get to here in a second. Right now, I want to talk to you about the other galaxy that we're working on, M82. Which is the Cigar Galaxy. It's this gorgeous galaxy with these crazy outflows and star formation in the center of the galaxy. Again, more parameters here. I'm going to kind of fly through this because I'm running out of time. But really interesting, lots of star formation and lots of outflows, and we're trying to figure out what's going on there. So we have this huge mosaic with JWST covering an even bigger area than what we have from HST. Here is the data catalog. I can't show you the image yet because that's coming from OPO here in a little bit. But right now, this is the gorgeous data catalog, and some science things that we can just pull out of this data catalog to start. This is a map of the CMDs across the face of the galaxy, broken up into regions like this. And there's this really interesting pattern where we're seeing in this region and this region, which are kind of on symmetric sides of the disk, or so you would expect. You can see that the stellar density is much lower on this side, and therefore the crowding is a lot less severe. And so we're able to pick out a lot more information in the CMD on this half rather than this half. And the same thing's true of these two components here. This is an indication of spiral arms in this galaxy. We're seeing exactly the region right here where this spiral arm kind of wraps over around each other and increases your stellar density and your crowding by quite a bit. So that's a cool thing that was never known before this project, is that this galaxy has a bar and spiral arms. Furthermore, the other kind of interesting science thing that we've pulled out of this is if we look at this very, very red CMD here, we can see there's some very blue sources here. And when we plotted this, when we plotted the locations on the sky of this, we can see that all of these very blue sources are coming exactly from the regions of all of that crazy outflow, as you can see here. So kind of looking at the center of either half of the disk, there's a lot of crazy outflows causing these blue sources. So some weird dust properties going on here. All right, I'm out of time. SED fitting, done with the beast. Talk to me more about it later. These are questions that we're hoping to answer by studying all of these galaxies, and I'll leave up with this if you want to look at this more. Thank you so much.
Thank you very much. We have time for one quick question. Hey, Janice.
Yeah, it's a great talk. F335W has PAH emission in it, right?
Yes, it does. So yeah, it's very possible that there's some interesting PAH stuff going on here that we're capturing along the sightlines of these stars. These are kind of throwing us for a loop because we didn't have these stars in our models, and so it's very clearly showing that there's very strong emission going on in those areas.
Very quick.
Yes. So in your summary slide, I saw that you are looking at, you plan to look at the metallicity gradient of this two, but not the metallicity gradient of the other one. And it would be interesting to look at the metallicity gradient of NGC4449 as well, because I did the gas phase metallicity. So, and I found an inverse metallicity gradient by looking at individual star-forming regions. So it will be interesting to see whether you get the same, because you would be looking at the photometry data and looking at the stellar population rather than the gas phase, gas nebula, right? The gas around the stars. So it would be interesting to see if there is a gradient there as well. That's all.
Yeah, we can absolutely do it. We can look at that data with the SED fitting, so we can definitely make those maps.
All right, let's thank one again. All right, I'm gonna present John while he gets ready. So the last speaker for the day is John Soltis. John is the last year data science postdoctoral fellow that started last year. John did his undergrad at the University of Michigan, and he has a master in physics and a PhD in astrophysics from the Johns Hopkins University that he finished last year. And his research is about applying machine learning to astronomy. So please take it away.
Thank you for the introduction. So like she mentioned, I'm a Lasker Fellow. I just started last year. And I'm going to talk about a project that I just started when I got here on trying to learn Gaia with machine learning. So first of all, just a little bit of background, although I'm sure almost everyone here already knows this. So Gaia is a space-based observatory. It's observed almost 2 billion different sources, mostly Milky Way stars and other nearby stars. It has precise astrometric information, angular positions, proper motions, parallaxes of these sources, as well as photometric information. And now with DR3 and with upcoming data releases, it's going to have even more information, including some spectroscopic information, light curve information, some radial velocities, etc. But for the purposes of the project that I'm doing today, I'm mostly just going to be focusing on the astrometric and photometric information. And so because it has all of this information on Gaia, or on Milky Way data especially, it's been extremely useful in both learning about the Milky Way, so the mass of the Milky Way, the structure of the Milky Way, learning about the Milky Way's dark matter halo. It's been useful for doing distance ladder cosmology, which is something I got to do myself when I was a graduate student at Johns Hopkins, using the tip of the red giant branch. And it's also been useful for identifying subpopulations and structures. So things like binary classification, exoplanets, stellar streams, open clusters, globular clusters, etc. And so the goal of my project, like I said, is to teach a machine learning model to be able to reproduce the Gaia DR3 survey, ideally to a high level of precision. And so you can think about this in kind of two parts. There's an unconditional version of this, where you have a model that just produces Gaia-like stars. And so you can sample that model as much as you want, and you should get distributions of parameters that look like the distributions that you would find in Gaia. And then there's also a conditional version of this, where you give it, like, say, the RA and DEC of actual stars in the Gaia survey, and then it should, based on that information, give you distributions of samples of mock stars that match those locations more than just the general distribution as a whole. And then finally, it would also be useful for being able to guess missing observations. So for a variety of reasons, there are times where Gaia doesn't have, say, the R band magnitude or the B band magnitude, or both of them, or a parallax. And this model would be able to then impute or guess, in an educated sense, what the parallax of that star should actually be, given both the parameters that are available and then also generally what it's learned about the Gaia survey. And because if you had a model that was capable of doing those things, again, to a high level of precision, then you could go back and do the same things that people have been doing with Gaia DR3 more generally, right? So if you could generate a bunch of samples of the Milky Way, then you could also try and measure the mass of the samples that you generated and compare that to mass estimates that people have made otherwise. Similarly, if you could sample finally the red giant branch population, for example, of like Omega Centauri, then perhaps you could try and get a measurement of the tip of the red giant branch there. And if you had a model like this, you could also use the information that it learned and its weights using its latent space to then try and identify subpopulations or structures in the real Gaia data. So again, then you could look back at like binary classification. You could look at structures like clusters. And so my motivation for this, and I think the motivation of the sort of machine learning cross astronomy community, generally speaking, has been to try and train machine learning models on these very large astrophysical data sets that are now available. And the motivation for Gaia specifically is both all of these exciting science problems that you can use Gaia for, and also the availability of it, its size. It's very large, right? It has almost 2 billion individual sources, but also is not very large in the sense of memory, right? So I can actually train a model on the entirety of the Gaia data set without having extreme computational resources available for me, whereas that wouldn't be true with other surveys. And then I also have the benefit of having worked with the data before, so I have some similarity here. So basically the point is it's ready to use, and it has sort of all of the benefits that we were looking for a large data set. And so how would you actually do this in practice? You would need a model that's capable of learning the complex distributions of the parameters that exist in Gaia. So when I'm saying parameters, right, like what are the distribution of parallaxes in Gaia? What are the distribution of positions on the sky of sources in Gaia? You need a model that's able to learn the combination of these distributions. And so how I do it in practice is I train a model that learns linear interpolations between a normal distribution and some target distribution, which again is just the distribution of these parameters in Gaia. And so in effect, what you're doing is you're learning how to draw straight lines going from this normal distribution, which you can easily sample, to the target distribution. And then if you've done that successfully, then you should be able to easily sample this normal distribution and then in effect be able to sample the target distribution, right? So you should be able to sample a normal distribution and get a realistic distribution of parallaxes that matches what you would expect for Gaia. And so in practice, what this actually looks like for me today is I'm only using 8 parameters, so really just the astrometric and photometric information from the Gaia source catalog. And I'm currently only training on about 1/3 of the data set, mostly just so that I can have models that run quickly. I give the model masked inputs, so sometimes I give it no actual information. That's where I'm talking about unconditional sampling. Sometimes I give it partial information. Sometimes I give it most of the information for a specific source in Gaia. And each time I give it more pieces of information, you know, I give it a position, I give it a parallax, then I'm hopefully conditioning the model to give me better and better guesses for that specific source. And then the model outputs are going to be the slope of these linear interpolations between the base and target distribution, which then I can use to actually sample the model and generate these mock sources. So what are the actual results of what I've been doing so far? So for unconditionally sampling the model, here I'm not giving, again, the model any information. I'm just telling it to basically dream up a bunch of stars that look Gaia-like. You can see that it's capable of like roughly matching the right ascension distribution from this sample of Gaia data, which is what I'm showing in blue, and the model is in orange. But it's also missing key pieces of information, right? So it's learning maybe some global information, but it doesn't actually have a high precision in this unconditional case. And so if I want to do things with the unconditional data like I was talking about, if I want to like measure Milky Way mass, this is probably not going to cut it. You can also see a fun example here. So now I'm showing the angular position on the y and x axis, and then in color I'm showing this g magnitude. This is the data again. This is samples from the model. It's not able to distinguish the LMC and the SMC. So it's seeing something, but it's not seeing it correctly. So again, not the level of precision that we want. This is a lot of progress from where I started. Hopefully more progress can be made. But for the conditional sampling, it's a lot more promising. And so conditional sampling, again, I'm giving it partial information. Maybe I'm giving it a position. Maybe I'm giving it photometry. It's able to do a lot better. So in this example here, what I'm showing is the parallaxes of sources from the model prediction minus the data prediction for when I give it positions and when I give it photometry. And so, you know, again, the precision could be better, but you can see, OK, it's learning conditional relationships between the parameters, which is what you would hope. It's doing better when you give it the photometric information than when you just give it the position. And more interestingly, then you can look at different combinations of conditional information that you could give the model. So again, this is like a position where now the color is parallax. And you can see, so this is where I'm giving all of those 8 parameters but parallax. So that means position, proper motion, photometry, but not parallax. And it's doing quite well, right? But it's even capturing like kind of small bits of information. They're matching. But you can see that when you give it less information, so here it's just getting the RA and DEC, now it's doing worse. If you give it just the photometry, now it's losing this distinguishing feature. If you give it both of those together, again, it starts to do a bit better. So there's some promising results here, but also some clear difficulties in getting the precision that you actually want. And so the next steps for this project, obviously, then are going to focus on seeing how and if I can improve the precision enough for the model to actually be useful. And so there's sort of 2 tracks for this. There are reasons for me to believe that the model itself may be limiting the precision. There are different things I can do on the machine learning side, technically speaking, to try and get a model that will more easily learn this target distribution that I want. But if it turns out that I'm sort of fundamentally limited there, the other option that I have is going back to those original problems that I posed. You could train a general model like this on specific subsets of the data. So like omega sun stars or white dwarfs, et cetera, and then apply it to those specific use cases. So that would be what I would call fine-tuning, which isn't sort of the ideal goal of the model, but is sort of the next best thing. And so in conclusion, I guess, the machine learning model that I'm trying to train on Gaia could be very useful if I get the ideal version of the model and I'm able to simulate Gaia observations precisely. And obviously, Gaia itself has been very useful, but currently is still a work in progress. There's some promising signs that I could improve the precision, and also there's some ways to pivot to improve upon it where it is. Thank you.
Great timing. All right, we have time for like a couple of questions. The back, sir.
Thank you for a nice talk. This is really exciting. This might fall under that fine-tuning you were talking about. Is there any hope that you might be able to sort of identify or classify like streets or stars that have been stripped of visual galaxies or visual clusters with this? By finding things that don't match the model or actually putting them in as an actual information of interest?
Yeah, I think that, again, if I did fine-tuning with the model, you could definitely use machine learning for something like that. I mean, with the current version of the model, I would not have confidence in its ability to do that. But I think that something like that is what I'm imagining would be sort of the final use case. Yes, yeah.
Yeah, you mentioned that you train on sort of a third of the data set, and 2 questions about that. One is it seemed like not training on 2/3 of it is good for having a test data set that's not in the training set. Do you agree with that? And the second question is, so how big is the computation? What's the runtime where you're running all this?
Yeah, so to the first point, the real reason that I'm only training on a third of the data set is one of the things that I wanted to try and do and that I had read about with machine learning models trained on these large data sets, like generative models like this, is that if you train it correctly and it's trained enough, you can demonstrate that it's not just memorizing the data, and in fact, it's learning some like true distribution. And so I wanted to split the data in half, basically, and have 2 training sets that were independent of each other, and then train 2 models, and then be able to compare samples. And then I found, working in one of the samples, that it was just much faster to train that than use the whole data set. But obviously, for a full case model, speaking to your point about data partitions, I would really want to train on like 80% of the data, use 10% of the data to determine when to stop training, and then leave 10% aside for testing. And then for your second point, which I think I've just lost track of.
How big is the computation where you're running it? Large?
So I actually, in like mid-October, got NSF Access grant, and so I've been running this on the San Diego supercomputer. Mostly I train it on a GPU. It depends on the size of the model, but you can, I would say, like completely train a model where it's not showing any improvement within a day. And some of the model variants that I've been working on, and this is one GPU, and some of the model variants that I've been working on recently can train even much faster than that. So it's not, and this is also, I'm like streaming through 32% of the Gaia data set, and it's able to do that. So I'm pretty happy with the computational side of it.
All right, we're at the top of the hour, so let's thank our speakers again.